this one right here, is his experiment where he took a coil of wire and he moved a magnet through the coil. And he found that when he moved a magnet through a coil of wire, it induced an electric current into the wire. Okay? So this led to the understanding that we now have that electricity and magnetism are deeply interconnected. They're really two sides of the same coin. So I have a little demonstration of this experiment, this Faraday coil, which was built for us by Jeff Lidgard in the Oxford Experimental Undergraduate Teaching Labs. So what we have here is a set of coils of wire, and through each of them, we've connected them through an LED. So if a current passes through the coil, we should get the LED to light up. Okay? And I have here a nice, powerful magnet. So if I drop it through here, hopefully, it's going to light up. How was that? Did it work? Good. All right, let's try it over here. Okay, we've colored them rainbow colors, so hopefully you can see one lighting up after the other. Here we go over there. Did it work? Okay, maybe. So it works. We've confirmed Faraday's observation that if you move a magnet through a coil of wire, you induce an electric current into the wire. Now, the converse is also true. If you pass an electric current through the coil of wire, you'll generate a magnetic field. So this gives us an inkling as to how it is these atoms can have their own little magnetic fields, these spins. Because if we were to take an electron, represented here by this ball of rubber bands, an electron, of course, has an electric charge, and so it has an electric field emanating from it. Okay, and so if I take my electron and I move it in a little loop like this, if we move our electron in a loop, then of course this defines a little electric current moving in a loop, because an electric current, after all, is just the passage of electric charge. So we take the electron and we move it in a loop, and that must then look like a magnetic field. And in particular, if I'm moving it in a clockwise direction, it should look like the north pole of a magnet. Okay? So if I were to move it in an anti-clockwise direction, it would look like the south pole of a magnet. So a deeper answer we can give to the question as to why we can't separate the poles of the magnet, thinking down on the atomic scale, is that if I take my electron and I move it in a clockwise direction to make it look like a north pole, and I continue doing exactly the same thing with my hand, but I turn around, then hopefully now it should look like it's going in an anti-clockwise direction, and therefore looks like a south pole. Okay, so now you see that the north pole viewed from one side is really just the south pole viewed from the other,